Is Stephen Wu. It's a pleasure to have you. Stephen Wu from Carnegie Mellon. Take it away.
All right. Thanks, Kostas. Let me know if my audio doesn't sound good in the room, because there's no other way I can know. But yeah, thanks to the organizers for having me at this workshop, even though I could only join remotely. So we want to talk about some of our recent work on imitation learning, mostly led by my excellent PhD student, Gokul. And also it has been a fun collaboration with Sanjaban Chaudhary and Drew Bagnell. And so Drew is also a co-advisor of Gokul. So both Sanjaban and Drew are also working at a local self-driving car company called Aurora. I would say the only bad thing for working with Sanjaban and Drew is that they kind of make me feel bad about my own time management. For example, Drew is a CTO of this company, and he still managed to have very much deep thoughts about research. But as a junior faculty myself, I find in myself often lack of time of deep thinking of research. Anyway, so this talk will be about imitation learning. Oh, by the way, the slides are mostly built on my collaborators, Gokul and Sanjaban's. So in order to talk about imitation learning, I think we should probably start with this general area of reinforcement learning. And as we see in this workshop, there has been a lot of theoretical advances and practical breakthroughs in RL. I guess one of the pivotal moments in RL is captured by this picture where AlphaGo was able to beat a top Go player. And I will highlight maybe two key elements behind some of these practical successes in RL. The first one, perhaps at least in the case of AlphaGo, is that it's relatively straightforward to specify an objective or some kind of reward function to indicate whether some player wins or loses a game. The second is that simulation of a goal, the game of Go or even chess, is relatively straightforward and fast. So you can simulate many plays of a game inside a computer many times very quickly. So arguably, Go and chess and games like that are quite different from many of the real-world reinforcement learning problems like self-driving cars or household robots, right? For example, for self-driving car, it is pretty difficult for good drivers to distill or enunciate a specific cost function or reward function that explicitly captures some kind of good driving. And exploration in real-world RL can be very challenging in some kind of unstructured real-world environment. But at the same time, in many of these real-world reinforcement learning problems, you would argue that there's actually lots of useful human demonstrations, right? So we have tons and tons of data about how good human drivers drive. So the idea of imitation learning in a nutshell, right, is to think about how to solve similar problems in RL, but leverage these, rich set of data of human demonstrations and interventions. Okay, so very quickly, the paper mostly based this talk on is a paper we had back in ICML, which is trying to think about how do you reason about different paradigms of methods solving imitation learning problem. So we try to provide a unifying game theoretic framework that sort of unified different ways of solving imitation learning problem. And the key technical centerpiece of our framework is the idea of moment matching, which is also at the heart of many problems and many methods in inverse optimal control or inverse reinforcement learning. And what's nice about this framework is that it sort of allows us to think about a family of reduction-based algorithms by thinking about solving imitation learning as a kind of game solving. So we can actually think about different types of adversarial learning techniques, which is sort of the emergent theme of this workshop. And also theoretically, it allows us to derive provable regret bounds, and the algorithms also have pretty nice practical performances, right? So this is our contributions in a nutshell. So to put our contribution more concretely, let's give a little bit of notation. So I try to avoid using too much notations in this talk, but imagine you have some kind of learner deploying some kind of policy, making decisions in a Markov decision process. So some kind of MDP, right? So you deploy a policy in an MDP, you will actually generate a trajectory, which is just a sequence of states and actions. And what you're concerned about is usually maximize some kind of reward. So there's usually an unknown reward function that maps state action you taken in that state to some real value. Typically it's unknown, and in imitation learning is actually unspecified. You may never observe a reward ever. And also the way the MDP determine how you transition from state to state is determined by some kind of transition kernel. Quite often time this is also assumed to be unknown. But in many cases, at least in self-driving car scenario, I believe in companies like Aurora, they actually build very powerful simulator. So sometimes you can actually assume people know how the transition work, even during training time. Okay, so similar to typical reinforcement learning problem, you also want to maximize your long-term performance, which is really just the sum of the per round rewards or the cumulative rewards. So what is imitation learning trying to solve? In a nutshell, really, it's about the following. Right. So the learner is given demonstrations from expert policy. So you observe how an expert solved some problem, right? Solve these underlying RL problem, and you would like to learn from the data, learn from these demonstrations, some kind of policy that sort of maps state to actions, so that your performance gap or the imitation gap, that is the performance between the expert and the performance of your learner's policy, the gap is small. So you want to sort of close the gap or the regret as small as possible. Good. So we're not the first one to think about imitation learning. There's a long history of how people solve imitation learning. But I would like to give you a quick maybe overview of how some of the methods solving what are the major paradigms. There are roughly 3 classes of methods, and I will roughly categorize them based on whether the algorithm have access to some kind of human experts doing training, and whether the training algorithm have some kind of access to either the environment or the simulator during training time. Okay, so perhaps the easiest way you can think of solving this problem of imitation learning is, a paper back in maybe the late 90s and late 80s and early 90s. I think later we coined this algorithm as behavioral cloning, which is perhaps the most straightforward thing you can think of, which is just you collect demonstration from expert on how they solve this problem, right? So in this case, I'm stealing a picture from Spencer et al. One of the authors, providing demonstration on how to drive a car, even though the car is kind of small. So you collect all these data on how human is driving this car, and you basically just treat it as a supervised learning problem, right? So you have sort of the state or the features of the states, that's sort of the data, input data to a classifier. And you have the action taken by the human, which is sort of the label you want to match, right? So you basically treat it as a supervised learning problem, and you want to have some kind of policy or classifier that drive the training error or the validation error to be small, something like Epsilon. Okay, so what you get is basically what people like to call the behavioral cloning policy. So how well does it work? So in this case, I'm stealing a video from the others as well. So this is how a behavioral cloning policy will work. It actually, I think, crashes into a wall somewhere in Princeton. Okay, so why did this policy crash the car, right? So it's actually not hard to believe why that could happen. So one way you can visualize this is, the learner is actually incurring some amount of error in the supervised learning objective. Roughly speaking, at every time step, there's sort of epsilon chance that the robot or the policy might deviate slightly from the expert trajectory. Okay. But as soon as the behavioral cloning policy does that, it sort of freak out in some sense, right? Because it put the car in a situation where they have never seen any kind of training data. And here you basically the car doesn't know where to go because the policy actually never seen such a state before, and it may actually keep drifting away. So every time step over the horizon of t steps, you have epsilon chance to incur linear in t regret. And over time, if you do the proper accounting, you actually have quadratically in t, the time horizon in the imitation gap. So you actually accumulate epsilon t squared imitation gap compared to the expert policy. So this is sort of a well-acknowledged, well-aware phenomenon in imitation learning. To summarize, it's really a phenomenon of how the feedback compounds errors. So as soon as you have a slight distribution shift from the expert, this error due to distribution shift will compound, and it compounds quadratically over time. Okay, so, and obviously people have thought about how to fix this issue, right? So how do you fix this kind of compounding error? One way people have thought about doing is, well, maybe you should invite the expert to involve in the training process. So you actually, they can provide some kind of interactive feedback. So one of the algorithms of doing that, perhaps one of the first algorithms, a classical algorithm called Dagger, standing for data set aggregation, is trying to do that. So I'm going to try to show that pictorially, right? So what Dagger is doing in the first step is sort of similar to behavioral cloning. So you try to collect how human drives a car, right? So you collect all of these demonstrations from human driver. So you have some warm-up data to begin with, and you also train in policy sort of as a supervised learning problem. So you have some kind of initial policy. But we know just doing that, it doesn't work, right? It doesn't avoid this cascading or compounding error. So what you do later is to basically now deploy this policy, right, in the environment. And as soon as you notice that you actually have some form of deviation from the expert data, you basically let the human come in to correct the behavior. Okay? So as soon as it deviates from the expert trajectory, the human expert will intervene and actually, through some kind of controller, for example, correct the trajectory. Okay. And this way you allow the policy to keep collecting data, right? So collecting the data of the form that as soon as the robot deviate, how human intervene and correct for it. Right? So this is how aggregate data work and allow you to accumulate new data and keep training. Okay. And you can do that over many iterations, keep letting the human correct the policy. And after some number of iterations, the policy or the robot will drive more smoothly, behaving much more like a human expert. Okay, so here the solution for solving this cascading or compounding error is basically interactively query the expert during training. So basically, what Dagger is doing is keep rolling out this learner to solve the problem, and have the expert to have some kind of hand holding on the learner. While doing that, you keep aggregating data and accumulating data to train a better policy. So in this way, you actually can avoid this kind of quadratic in time horizon sort of regret or imitation gap. So you have sort of epsilon t imitation gap. Right. So if I tell you this algorithm, I think one thing you might complain about Dagger is that, well, this is all nice and good, but it's too much effort for the human, right? So it's too much effort to have this kind of hand holding during the entire training process. Basically, you have some kind of watchful expert looking at every time step of the rollout of the learning, right? So it's a lot of effort. So oftentimes there's a third paradigm, which is the last paradigm we'll cover.
So Stephen, can I ask a question just to clarify a little bit?
Please.
So you have this epsilon times t. Can you specify a little bit what is epsilon, what is t? I mean, like are you thinking of a
Yeah.
model where, like, how are the errors injected, and like why, like is this epsilon t time good, or you can hope to do better? Like, so what is the? Could you explain
it's
a little
it's a
bit
good
the
question.
model? Yeah.
Yeah. So epsilon, unfortunately, will have some ambiguity in the talk. So I will explain what this means, but later on, epsilon will appear, will have a different meaning. So here, epsilon is the supervised learning loss in this setup. So think about this as a supervised learning where you keep rolling out expert trajectory, keep collecting data from human corrections. So you accumulate a large data set or over multiple rollouts, and you try to fit a policy to minimize that supervised learning data set. And you will have epsilon fitting error. Okay. That's assuming you don't get perfect fitting. And that the epsilon is coming from that supervised learning loss. And epsilon t is sort of the best you can do. You cannot do better than this. Because
So,
if every round you still have epsilon chance of deviating, the best you can do is epsilon t.
yeah, so then like, so how did this epsilon t squared arise? Because kind of like I was thinking that, like, why can't you couple the trajectory of the human and the, epsilon suboptimal policy to say that over t steps, I can couple them so that they are, I don't know. I mean, I guess it's not you're not sampling, you're doing something else. This is distance. What is the epsilon t squared? This is.
So this, if you have interactive expert, you won't have epsilon t squared. So let me go back really quickly.
Yeah, without interaction. Why is it epsilon t squared?
Yeah, so by the way, epsilon t squared is also, in the worst case, you have to pay for that. So one iteration very quickly is that, let's say you only look at the first t over 2 time steps. And in every time step in the first half of the horizon, every time step you have epsilon probability of deviating from expert trajectory. Okay. And as soon as you do that, you pay for the entire time horizon. Like you pay for linear and t regret. So you can avoid some time step, but an expectation, if you sum it up, but every time you deviate, you pay for sort of t regret, like t over 2.
So this is the reward that you're tracking. Okay, got it. Yeah. Okay, so you're compounding reward errors. Okay, thanks.
That's right. Yeah, thanks for the question. Any more questions? Oh, this is kind of... Sorry for the simulation. All right. Okay. So one issue about this kind of interactive expert sort of setting is that it involves too much human effort. So sort of a middle ground people have also thought about is only assuming some kind of simulator, or maybe you actually have access to the environment. So here you actually get to take both the expert demonstrations. So these are sort of offline data you have collected, but you can still keep rolling out your policy through a simulator. So, but without the hand-holding of an expert. What you can do at a high level, maybe you can still match the distributions. Even though you don't actually have a human expert in doing the training. Okay, so let me do a quick recap. So basically what we talk about is sort of 3 paradigms of how you might think about solving this problem. The first paradigm, sort of the example of behavioral cloning. So you only observe how experts solve the problem. So you only have data collected and that's it. And the sort of the thing you can do is do some kind of supervised learning, treat it as a supervised learning problem, but you might suffer this kind of compounding error. The other kind is sort of what Dagger was doing, is invite some kind of interactive expert that roll out the learning policy, but keep correcting it over time. Okay, but it's very exhausting in some sense that the expert has to exert a lot of effort. And sort of a middle ground is you don't assume an interactive expert, but you actually assume some kind of interactive simulator. So you still have some access to the environment that keep allowing to roll out your policy. Okay, right. So I'm sort of new to imitation learning, but what we wanted to do in this paper is that, well, there are different kinds of methods you can think about to solve the problem, assuming different kind of access. So what we wanted to do is maybe come up with sort of a broad framework, in our case, using the language of moment matching, to think about how to design algorithms for these different regimes, for these different paradigms. And our hope is that, we actually want to derive some kind of performance bound that actually characterize the imitation gap in these different settings, and hopefully also derive practical algorithms motivated by some of these theoretical justification. Okay, so this is our goal, and I'm going to use the imitation gap as a guideline to derive the underlying moment matching framework. Okay, so what's our goal? So to recap, our goal is to train some kind of policy pi that try to imitate the expert policy really well, so that the imitation gap is small. Okay, so the imitation gap captured by some kind of performance or cumulative reward function J. All right, so this is well and good, but one challenge obviously is that the reward is unknown and actually unspecified most of the times. So the performance function is also unknown. So what do you do, right? So we actually don't know the objective we would like to maximize or minimize the gap. So taking inspiration maybe from a lot of work in this workshop and also adversarial learning, is that maybe we don't actually know what the performance function look like exactly, but we actually may have some kind of side information, or we maybe know what this a class function that might contain this objective function, this performance objective function. So taking inspiration from zero-sum game or Minimax game, what you can do is, well, instead of thinking hard about what J exactly look like, we can maybe simultaneously try to minimize the imitation gap for an entire class of functions that the performance function might belong to. Right? So we sort of can turn this into a Minimax objective. Okay. So let me give slightly more details, but all the intuition is captured by basically this slide. So a bit more concretely, you can think about basically three ways you can write out or decompose the imitation gap. Most obviously, you can basically plug in the definition, the vanilla definition of performance or cumulative rewards, and you can write this as basically sum of reward function for both the expert and also the policy you choose. Okay, so that's kind of obvious. But there are also other interesting ways you can actually rewrite this difference. So one very powerful tool in reinforcement learning, the performance difference lemma, also allow you to write this difference as a sum over the so-called advantages function, or the sum over the difference in the Q value function. So Q value informally just is sort of like a longer term perspective on reward. Basically, is the cumulative rewards you get by taking some action at some state and then following the policy pi from then on. Okay. If you've seen this before, you don't need to see a definition. But if you've never seen this before, this is the only intuition you need. Okay. So you can actually use the performance difference lemma to actually write it as the difference over the Q value functions under the policy, under the action chosen by the expert, and also under the action chosen by your policy. What's interesting is that the expectation is taking over only the expert trajectory. Okay, we'll revisit this objective again in a bit. There's actually another way to apply the performance difference lemma because it's sort of
one
symmetric.
question.
Yeah, go ahead.
So where does tau go in? Is it the typo? So you have like an expectation?
Oh yeah, sorry. Tau is the trajectory. So if the tau is like sort of like a sequence of S1, A1, ST, AT.
Okay.
Yeah.
Okay.
Yeah. Thanks. So you can apply performance difference lemma in a different way because it's sort of symmetric. So you can actually take expectation over trajectory coming out of your own learner's policy, and also compare the Q value function on these states, when you are taking action given by the expert, and also the Q value function when you're taking action given by the policy. Okay. So we'll see this objective again, but applying the same intuition we had in the last slide, right? The challenge with bounding these quantities that we don't actually know what R is, we don't know what the Q function is. But what we can do is that we can introduce maybe classes of function that if we know or assume contain these functions, right? So we can replace or upper bounds these objectives by introducing some sort of maximizer, maximum over some classes of function that contain either the reward function or the value function, the Q value function. Okay. So in particular, by doing that, you can actually sort of reformulate a problem nicely into 3 different minimax games. So minimax game between 2 players, 1 player controls which policy to deploy. The other player is sort of like the discriminator again that choose which function F to penalize the policy player. And what's nice about some of these minimax games is that if you think about the game values or the minimax value of these games, it upper bounds the performance difference between the learner and the expert. Okay. So let me organize this a little bit. So we actually have a naming for all these games, and in a second it will be more intuitive. The first kind of game is called an OffCue game. So it's offline because you're only collecting experts data. And what's important about this is that in the objective, you're only taking expectation over the expert trajectory. So these are sort of the data that's already given to you. So these are the expert wrote out trajectories that you have observed and collected so far. So importantly, in this game, you don't actually need access to any simulator or expert. Okay, so that's sort of the OffCue game because you're in an offline setting, you're only collecting observational data, and you would like to sort of match the Q value moments. Yeah. And the second one is sort of the reward matching game. So here you sort of requiring, in addition to expectation over the expert trajectory, you also have expectation over learners trajectory. So you actually require some kind of interactive simulator, and you also need to match moments that behave like reward functions. Yes, Vasilis.
Oh, so I didn't want to interrupt, but like since you stopped, so the previous inequalities hold it for the Q function. Is it clear, like, so if I do the soup over there, is it clear that the solution to this will achieve a small error with respect to the original objective? Because now maybe there's some terrible F in there. Like, is there a policy that will make this 0 for all F?
Yeah, they may not. I think, yeah, you're asking a more in-depth question. I think the short answer is if you have near realizability or realizability, yes. Without realizability, it's challenging, yes.
So suppose that there is a reliability, you mean that the true Q function lies in FQ?
So if the policy class pi include pi e, then you can always just play pi. Like a minimax strategy could just be pi e. That is always 0. Yeah. Yeah.
I see. Okay.
But that assumption may not hold true, and there's an issue that I don't think. Yeah, this paper addressed clearly yet. Yeah. Thanks. So, but lastly, there's a third type of game, which is we call it OnCue game, which is sort of the most demanding in terms of access to both requiring a simulator and also an expert. So if you look at the objective, it's sort of obvious in the sense that it requires taking expectation over the learner's trajectory. So you require rolling out the learner's policy, but also you also need to query the experts along the way of the states visited by the learner. So you require both interactive and simulator, interactive expert and simulator. And here you're also trying to match some kind of Q value moments. Okay. So what's nice about some of these Minimax formulation is that it's sort of capture or recover some of the special cases, some of the previous algorithms, the special cases, or well aligned with some of these other algorithms. Like, so for example, in OffCue Game, where we're trying to minimize divergence between the learners and experts' actions on the states visited by the experts' trajectories, this is sort of reminiscent of algorithms like behavioral cloning and value dice. In the OnCue Game, where you're minimizing the divergence between learner and expert actions, but now on the states alongside of the learner's trajectories, it's sort of mimic ideas like a dagger and other algorithms. And the reward matching game, I think you minimize just the divergence between both the entire trajectories by learner and expert. So that's sort of aligned with some of these algorithms like Gale and Squill. Okay, so and what's nice about the game theoretic framework is that also give you a whole family of ways to solve this kind of problem by treating it as an equilibrium computation problem, right? So one thing you could show is that if you have an approximate equilibrium in these moment matching game, you also should be able to solve the underlying imitation learning problem. So very quickly, we'll think about the concept of basically epsilon approximate equilibrium. Okay, so roughly speaking, it's just like a pair of strategies, one given by the policy, one given by some discriminator F, so that no matter which player decide to deviate and take on another strategy, whether it's a policy or a discriminator, any player can now gain by more than epsilon. Okay, so so one thing we can show is sort of a way to translate guarantee from computing a approximate equilibrium of the game to a performance or imitation gap in the imitation learning problem. Okay, so for
Steven,
these,
sorry to interrupt. So
yeah, go ahead.
It's a bit unclear to me, like your family F, does it depend on the expert policy?
In some cases, yes. So in the reward and the off, it's the OnCue setting, it does, yes. So I guess maybe a better way to answer is I only need to assume that the expert policy's value functions belong to the class of F, which I'll get to in 2 bullet points. But does that answer your question?
Kind of. So I guess my question is like, the expert policy is supposed to be something that does well with respect to the true reward, right? So,
yes.
So is that sort of reflecting in the class F?
Yes. Yes, as in, the F should contain the value functions by the expert policy in one of the cases.
But also it should not include things that the expert policy is terrible, right?
I think it's related to what Vasilis was asking.
Yeah.
I guess like if the expert is terrible in some terrible reward function, I should be matching that terrible value. So in some sense, it doesn't matter. Yeah. Does that answer your question there?
Not sure, but
No, yeah, maybe following up on that, like, so what if my function class F contains the value function of some terrible policy, not the expert policy?
Yeah.
Then in some sense, I'm also trying to imitate that terrible policy. So what
So
am
the
I
F is not policy.
here?
So maybe a quick clarification question. F is not capturing policy, but capturing something like rewards or a value moment.
Yeah, but it's like the value at under the expert policy, right? It's trying to capture that. Like they say the Q function under the expert policy, or the value function under the expert policy.
So maybe it's easier to think about reward first. Like value is a little tricky to think about. Before reward, right? Like, I could do terrible. Like expert policy, the real expert policy can do terrible according to some reward. And I should be matching that moment under the expert policy. So in some sense, I should not deviate from that expectation.
So Stephen, I guess what you're saying is if the expert policy performs poorly on some reward, you are still asking your pi to match that on that terrible reward.
Yeah.
But you don't have to, right? You can say these are terrible, these rewards are not going to show up because the expert is actually should be doing well. So let's forget about those in my class F.
We don't have to, but I guess it's a stronger guarantee. Like I think it implies that, on the actual reward, you also do well. Yeah. Like solving a minimax problem is like strictly harder than directly giving you a reward function and solve it.
So I guess like if the policy class contains at least the expert policy, and if I make no further assumptions, the best epsilon I can hope for is something like root t, as in whatever I'll get from some martingale argument that like if I follow.
Let's say like even without sampling error, right? Like one of root t coming from sampling error.
Right. I mean. Yeah.
Yeah.
I see. Yeah.
Let's not. Yeah.
Let's not think about that. Okay.
Maybe that's like a little distract. Yeah. But if you can perfect evaluation of expectation, realizability, and infinite samples should buy you epsilon equals 0. Okay. I'm happy to discuss more, but I want to keep going because I think it's running a bit late. Actually, I'm way behind. Actually, do I have until the end of the hour?
Yeah, that was the original plan, but you can get another 5 minutes.
Okay. All right. Maybe I have to skip some of the steps. But one nice thing about this equilibrium structure is that you can actually translate the approximate equilibrium guarantee into some of the guarantee on the imitation gaps. And in the off-Q setting, you actually expect sort of a quadratic error. In the on-Q setting, I think it's a little more subtle. The balance a bit more nuanced in the sense that it depends on also another parameter that's on the class of functions, which we call it H recoverable. It's a little mouthful to state the definition here, but roughly speaking, sort of requires the expert take the expert H steps to recover from any mistake. So if sort of capture the idea that if your learner policy deviate from the expert trajectory, by following the expert's policy, you can actually recover in H steps. Okay, and we can actually prove some of these matching lower bounds at least on the dependence on epsilon and t. Okay, so this is a formulation of Minimax games, and I think many people in the room know how to solve Minimax game quite well. And one of my favorite ways to do this is sort of perform some kind of no regret dynamics that sort of perform some kind of repeated plays over n iterations. And the policy player will basically iteratively update some underlying policy, and the discriminator will iteratively pick some kind of moment functions to penalize the policy player. Suppose they both are trying to minimize some sort of cumulative regret, given by sort of the cumulative reward of cost they achieve over some iteration, compared to the best benchmark in hindsight. one well-established result in Minimax and games and also online learning is to show that if the regret is growing sublinear in a number of steps, you also are able to compute approximate equilibrium of the game. This will sort of allow us to think about different recipes of designing algorithms under this kind of no regret versus best response kind of algorithm. So you can actually have some freedom to choose whether you decide to implement some kind of no regret algorithm on the policy player or have the no regret algorithm play on the discriminator player and let the other player best response everyone. Okay, so I think this workshop I've seen a lot of these kind of algorithms. And so one quick result we can prove, sort of a theoretical result, is you can actually provide some kind of reduction to this kind of no regret oracle or best response oracle and solve this kind of Minimax game, all three kinds of Minimax games under polynomial iterations. You have to do a slight bit work from the standard framework, but I think the proof is not too surprising from for those who are used to thinking about solving games using no regret algorithms. I think what's more interesting about this result is that it allows you to think about some kind of paradigm to design practical algorithms. So arguably in practice, you probably don't want to implement provable no regret algorithms like follow the perturbed leader. So you can think about some sort of neural network or gradient based optimization. So you can actually do that by reconfigure some of the subroutine by replacing some of the more powerful solvers in reinforcement learning. So for these three different games, I think we're able to come up with three different algorithms. They kind of have funny names because my student Gokul like to be creative in coming up with names. They call it Advil, Adril, and Dayquil. I think it takes a little while to understand why they call that. In fact, as the advisor, I was a little worried about student because it looks like the student has spent too much time in the pharmacy. But the algorithms work pretty well practically. I think on three different tasks, I think they under different assumptions of whether you have access to environments or the expert, they tend to outperform some of the standard benchmarks. Okay, so I'm about to run out of time. I want to quickly wrap up a little bit. So to summarize for this paper, I think what's nice about this is it's kind of like a nice game theoretical framework to think about all these three paradigms of how to solve imitation learning. And you can derive different kind of imitation gap. And what I didn't touch on is you also have different kind of sort of computational requirement for how to solve the underlying game. Notably, the reward matching type of algorithm, the most natural algorithm we are aware of so far tend to involve solving some kind of planning problem. So basically, when the discriminator gives you some kind of adversarial reward, you have to solve some kind of planning problem over the MDP defined by this reward function. What I didn't have time to touch on, actually, our paper didn't fully resolve is, related to Costa's question, where does this epsilon come from? Right? I think so. The epsilon in the definition of our paper sort of corresponds to the approximate equilibrium parameter, right? So sort of the moment matching error defined by the Minimax game, but we didn't really account for where it come from, which could come from roughly three sources. Could come from statistical error, like how do you estimate the expectation of these moments, and it could be coming from some sort of error like non-realizability, like approximation due to limited function class, and it could come from maybe like approximate optimization of your solver potentially. So all these questions worth studying. I think we slowly making some of the progress along these lines. For example, in a recent collaboration between our team and a group of researchers at Berkeley, I think the lead co-authors, the student co-authors, Matthew Pong, Gokul and Nivet Rajaraman, we start understanding, in some of these settings, what exactly the statistical complexity. What's the optimal sample complexity when you start making some of these assumptions, such as realizability or a deterministic expert, to isolate the statistical complexity of the problem. And maybe one nice takeaway is that you can think about some sort of more interesting algorithm that doesn't directly just apply moment matching, but some sort of hybrid algorithm that combine some of the idea from behavioral cloning and moment matching. I think I'm sort of out of time, but Gokul also has been making progress in thinking through some of these imitation learning problem under unobservable confounds. One nice result we had is thinking about how to combine the idea of adversarial learning and instrumental variable regression in the imitation learning setting. So there's actually a nice, also sort of game theoretic type algorithm for solving this kind of imitation learning problem under unobservable confounds. But I guess I will skip this. I'm happy to discuss offline. So in summary, I think our work sort of make a nice case study related to the theme of the workshop, which is thinking about adversarial learning and moment matching can be a nice recipe for deriving imitation learning methods. And there's still a lot of understanding we need to do to figure out the computational statistical trade-offs under different imitation learning paradigms and assumptions, which our work doesn't fully address yet. And I think interesting open directions that we are very excited about is whether you can apply this kind of adversarial learning techniques or game solving techniques from the Minimax perspective to solve some of the harder imitation learning problems. For example, maybe there's unobservable confounders in the expert demonstrations, or maybe the experts are not necessarily perfect or have some kind of defects. Okay, with that, I would like to conclude my talk, and thank you for all the questions.
Any questions for Stephen? Yeah.
Yeah, hi, Stephen. So I think it's really interesting to see that all these three paradigms of imitation learning can be all framed into Minimax optimization. I was wondering, like, also kind of coming back to the question by Vasnis is like, so of course the way how you choose this function class F, right, for the test function or discriminator affect the optimization error, affects the statistic side. But I was wondering, like, in your result, you've shown that this compounding error has nothing to do with kind of how you choose the function class, but only depends on realizability. Is that the case?
For the compounds result, which I guess I didn't talk through much.
No, I mean the compounding error, that part.
Compounding error.
Yeah, where there it doesn't really depend on whether, like, how large is the function class, but rather just on the realizability assumption, right?
That's a good question. So I think even under realizability assumption, I think the compounding error in the purely offline setting is unavoidable. Because even if your policy contain the expert's policy, even if the class of functions, the discriminant class of function contain the true value function, there's still a chance of this kind of epsilon error accumulate over time because of finite sample. Because of the finite sample you only see in the expert data. So in a way, as long as you're not solving this underlying supervised learning problem or the moment matching problem perfectly, that error will compound quadratically over time. So that, I think that's still going to happen, even if you make realizability issue. I think you can avoid that if you have both realizability assumption and also infinite sample assumption. Then you can avoid the compounding error. Yeah. So this is why behavioral cloning could work.
So I do have a second question is like, I think in general, like this reward matching or this inverse RL where you try to learn the reward, it is also known that it's kind of ill posed and oftentimes you need to add some regularization, right? So for instance, max entropy, etc. Like here, like, do you see any like a need to add like some regularization either on the function class or on the policy side to improve the performance?
Yeah, I think implicitly, I think actually explicitly, some of the algorithms actually do that. I think, especially in this last work we mentioned, we actually have regularization on the discriminator class. And I think, some of the, experiments definitely rely on, maybe not explicit regularization, but, like slow learning rate. Yeah, so definitely, I think that plays an important role, at least in the practical performance. I think that's a very good point.
No, yeah, thanks a lot.
Thank you for the question.
So I had a question about I think Vasilis also has one. So I had a question about your the no regret learning you mentioned. Like, are you returning distributions over policies and distributions over Fs, and you're playing a mixture over policies? I mean, your problem isn't convex, or is it? I mean, it didn't look like it's convex.
Yeah, very good. So I knew someone was going to ask this. Probably game theorists will ask this. But first of all, I think depends on how you view the policy. So one nice way to view this kind of problem is to think about in the space of occupancy measure. Like if you have a policy, it can correspond to a state action distribution, a distribution over state action pairs. So you can think about that representation. If you think about that representation of the policy, and everything is linear. So basically, like you're actually assigning value to every state action, everything is linear. So in some sense, the nicety of Minimax theorem still holds. But your question is, you probably should be, if you play no regret algorithm, you probably will be playing mixed strategy, which will mean mixed policy. So theoretically, I don't think it matters. I think there's a well-known result by Umar Syed, Michael, I forgot his last name, and Wap Shapiri, that basically tell you if you can take the mixed strategy, write down the occupancy measure, which is distribution over state and actions, you can rederive a single policy that matches with the state action occupancy measure. So you can always, without loss, to assume that you have the same singleton policy, at least theoretically. In practice, we don't actually run like multiplicative weights.
So in practice, you do gradient descent parametric.
We have to do some kind of gradient-based optimization. Yeah.
Okay.
So if you have your hand up for a while.
Yeah, my question was more like on the practical. So like like for example, like is Gokul or Andrew applying these types of algorithms in like self-driving cars? And if so, like how do you choose an F there? Like what are the types of Fs that function classes that people choose? Are they? And how are they informed by domain experts or something?
Yeah, I think it's a challenging question. So I think the honest answer is I don't know. I can tell you what we did in experiments, which are mostly given by two-layer neural network, and maybe some form of RKHS. But in self-driving car domain, I don't know. I think you have to incorporate some other side information, like hopefully the F should incorporate ideas like you should not crash into the car in front of you, like that should. Like aspect like good driving that should be captured into this kind of function class. Yeah.
I see. Okay.
Yeah.
But then if you're so that's so you're allowing it to be very powerful in some sense and unmodeled. Like if you're in the unrealizable case and say under the true Q function or value function, you have an epsilon error. By moving to the soup over F, that could be blowing up because maybe there's some other.
Be a worry. That would be maybe a drawback in thinking about super expressive function class. I do think that's an interesting trade-off that maybe is related to all the questions you had with Yan that we did not address well. Like, because like the game value will be also large in that case. Like it may not be close to 0.
Exactly. Yeah.
Yeah, I think that's
if
great.
you allow for unnatural test functions, then yeah, you could have like a huge game value in the unrealizable case.
Yeah, I think that's an interesting trade-off in for IL.
All right, so I think we reached our capacity for the day. Thank you very much, Stephen, for keeping our interest very active, even at this advanced time. And also, like, thank you for staying up, postponing your dinner plans and this goes for talking to us. Thank you very much.
All right, thank you.